lecture, we have seen the partial wave method to find the uh, total scattering cross section. Uh, that is part one. Now we will see the same partial wave method part two. I will explain what is difference between my previous lecture and this lecture. My previous lecture, that is the partial wave analysis part one. We have seen the total wave function psi, which is a function of r and theta, is equal to a into e power ikz plus k into summation over l I power l plus 1 2l plus 1 al, that this is a partial wave amplitude, and hl of hl1, which is a function of kr. This is the Henkel function of kind 1, and PL cos theta. This is the Lth Legendre polynomial. Uh, Now here two important thing to be noted is in previous lecture we have considered only the scattered amplitude, that is the uh, second term. We have considered only the second term. So actually, the outgoing wave consists of both incident wave as well as the scattered wave. Uh, but however, you can notice this, that is the first term is in Cartesian coordinate and the second term is spherical coordinate. So we can rewrite this expression using spherical coordinate by using the expansion for this exponential, that is first term. First term in Cartesian coordinate is e power ikz, which is equal to in spherical polar coordinate summation over L 0 to infinite I power L into 2L plus 1 into JL into PL cos theta. Now you plug in this into the first term. That is, this will become summation over L. Uh, this term, you can keep the this term as it is. I have plugged this term here. So this will be shown here. So here both terms are summation over L. So you can combine this. You can take the common term out. Here common term is IL. This can be written as IL into I. So IL 2L plus 1 uh, PL cos theta. The bond which I have shown in red color is common. So I have taken 2L plus 1 PL cos theta and this I power L. Here it is I power L plus 1. So this can be written as I power L into I. So that I have taken here. Already there is a K. So this will become, this can be rewritten as psi, which is a function of r and theta, is equal to summation over L, IL 2L plus 1 JL plus IK AL HL1 into PL cos theta. So now we have converted all into spherical coordinates. The exterior solution may be written in spherical coordinate as psi, which is a function of r and theta, is equal to summation over L I power L 2L plus 1 into JL plus IKAL HL1 into PL cos theta. Here it is important point to be noted that is the amplitude of the incoming wave must be equal to the amplitude of the outgoing wave by using the conservation of probability. At all angle, the probability of number of particles scattered is we have taken that is spherically symmetry, so it is independent of pi. So the incoming wave, the amplitude of the incoming wave must be equal to the amplitude of the outgoing wave. You know very well that the square of the amplitude gives you the probability. So it must be same in order to have the same probability. So we can reformulate our scattering problem in terms of calculating phase shift. This is very important point to be noted. That is phase shift rather than the partial wave. We will take the amplitude of the incoming wave and outgoing wave is the same. Only there is a difference in the phase factor. So now we are reformulating our problem. In terms of phase shift, the partial wave amplitude is defined as AL is equal to 1 over 2ik e power 2I delta L minus 1. This delta L is the phase shift of Lth partial wave. Uh, which can be written as 1 over 2ik e power I delta. This 2I delta I am separating out. That is e power I delta into e power I delta. So then naturally the second term will become e power minus I delta L. So that if you multiply these two, it will become 1. The terms in the bracket is equal to 2I sine delta L. We know that is e power I delta L minus e power minus I delta L is equal to 2I sine delta L. This 2I will get cancelled. You will get to 1 over k e power I delta L sine delta L. Then the scattering amplitude will become 2L plus AL. Instead of AL, we are replacing 1 over K, which I have shown in the red color part, e power I delta L into sine delta L and P cos theta. Only thing I have done is here in for AL, I have plugged this equation, this expression. So this is the scattering amplitude uh, which include the incoming wave and the scattered wave. So it's a combination of incoming wave and scattered wave. We have taken only the phase is there is a phase shift, no change in the amplitude. And then the differential cross section is given by T sigma over T omega is equal to modulus F squared, which is equal to F into F star. We have seen that F is equal to 1 over K summation over L 2L plus 1 e power I delta L sine delta L PL cos theta. Then the differential cross section is equal to F star. Just now I have explained. If you multiply F by its complex conjugate, this is the real number. So this will become 1 over k into 1 over k, which will become 1 over k squared. And the this term 2L plus 1 will become, we are summing over L and L prime. So 2L plus 1 for F star, you will 2L prime plus 1, and this is e power I delta, and its complex conjugate is e power minus I delta. Similarly for this one, sine delta into sine delta prime. Similarly for PL cos theta, PL prime cos theta. Here I have explained, if you in order to find this is the differential cross section. In order to find the total cross section, you have to integrate it, and you have to apply the orthonormal condition for integration of PL cos theta, PL prime cos theta, which I have explained in my previous lecture. Of course, this is equal to 2 divided by 2L plus 1 delta L L prime. That is delta L L prime is Kronecker delta. So the summation exists only when L is equal to L prime. So this will become 2L plus 1 into 2L plus 1, which is equal to 2L plus 1 whole square. This term will become 1, and this is sine squared delta L. Uh, then I have informed that this is equal to 2 into, if you integrate this, you will get 2 divided by 2L plus 1 delta L prime. So 2L plus 1 will cancel with this 2L plus 1 squared. This will become 2L plus 1 delta squared, sorry, sine squared delta L, and 4 pi. After integration and simplification, you will get the total cross section sigma equal to 4 pi over k squared summation over L, 2L plus 1 sine squared delta L. This integration part I have already explained in my previous lecture, that is partial wave analysis part 1. You can refer my previous lecture. Now we will see about the low energy scattering. In the study of low energy scattering, where at most two or three values of L are important, we can ignore the higher L. If the energy is so low, uh, that is only S state is involved. The theory is especially simple. In this case, all the spaceships except delta 0 are negligible, then the scattering coefficient f, which is a function of theta, is equal to 1 over k uh, summation over L, 2L plus 1 e power I delta L sine delta L PL cos theta. That what we have seen. Uh, when L equal to 0, this will become 1 over k, and this is first term will become 1. This will become e power I delta 0. This will become sine delta 0. The P is 0 when L equal to 0, PL cos theta is equal to 1. That also we know. So that f of theta can be written as 1 over k e power I delta 0 sine delta 0. So naturally, and the total cross section is given by sigma is equal to 4 pi. After integrating this, you will get sigma is equal to 4 pi over k squared sine squared delta delta naught. Here you can see this total scattering cross section is independent of angle theta. We have seen that the amplitude of the low energy scattering is equal to 1 over k e power I delta naught into sine delta naught. The scattering amplitude here, if you look into the expression, you can find that the scattering amplitude and therefore the differential cross section, because the differential cross section is nothing but modulus square of the amplitude, square of this amplitude, which is independent of theta. That means the scattering is isotropic. Since we are dealing with very low energy, the wavelength associated with the incident particle is very long. Because the energy is very low, low energy, that means the wavelength is very high compared to range of the ports. We assumed that potential is localized. So that means the range is very small comparing the wavelength of the particle. And the direction of incident is directed by the scatterer by means of the difference in phase of incident wave between 2 points separated by a distance of r naught. If R naught is a small fraction of the wavelength, the phase difference is inappreciable, and the direction of incident does not matter for the scattering. So these are the some of the important points about the low energy scattering. Thank you very much for watching my video and supporting me continuously.